次のセッションですが、実用的な言論入門ということで、ダニエラさんにお話ししていただきます。よろしくお願いいたします。
Okay, can everybody hear me, yeah? Okay, cool. Thank you guys for having me here in Japan. It's been awesome. And today I would like to talk to you about category theory. So this is going to be a long talk. So it's not just going to be me talking. We will also do some code. If you have your laptop, great. Feel free to follow me. If not, I'm afraid I will have to do all the work. Okay? So if you have your laptop and you are willing to code with me, make sure to go to that URL and clone the repo. I'm going to do a little bit of introduction to give you guys time to download the internet. And please make sure to just do SBT and then compile. If compile works, all good. Don't worry, there is just one dependency. There is ScalaCheck. So hopefully we're not going to break the Wi-Fi of the conference. Sounds good? Awesome. OK, then let's start. So this talk is going to be an introduction to category theory, but it's going to be a little bit different than usual. This is the topics that we are going to cover. We have plenty of time. I'm going to try to go slow. And hopefully, we will manage to cover all of them. OK? So we will talk about a little bit about category theory. What is it about? Why has developers we should care about it? And we will talk about crazy things like monoid, functor, applicative monad. I know those terms are really scary, but bear with me, we can do this. So first of all, hi guys, I'm Daniela, and I did Java for a long time, and I loved it. And then I discovered Scala, and everything changed. So I'm not a mathematician. I did computer science at university. So I found myself suddenly with a lot of object-oriented knowledge that was basically useless. Everybody was saying, no, forget about it. It's not cool anymore. Now you have to talk about functions and functors and monad. And I was like, what? What is that? So it was painful. I'm not going to lie to you. I started studying a little bit. And I discovered that all these mathematical principles are super cool. It happens that I'm writing a book, but this talk is not about my book. If you guys want to come and talk to me, I'll be more than happy to give you information about my book. But the point of this presentation is that I'm not a mathematician. So for a long time, and to be honest with you, even today, every once in a while, I go to a conference, and people start talking about optics, functor optics, and I start to cry. Because I have no idea what all these crazy things are about. I kind of guess what a mathematical formula is about, but I have to read it like 4 or 5 times before I actually fully get what it's about. The way my brain has been trained to think is through images and through comparison with the reality. So when I see a big formula with a lot of symbols, my brain goes, whoa, what the hell is happening? So that's why I have decided to do this presentation for people like me that are not mathematicians, because I do believe these concepts are really important for us developers. And I'm not going to explain them from a point of view of a mathematician. So if you are a mathematician, I do apologize, because I'm going to say things that you guys are really not going to like. They are imprecise, but they are enough for us developers to understand why things work in a certain way. OK? So first of all, why do we care, right? Why should a developer go back to school and study this mathematical theory? Well, I'm going to give you my motivation of why I did it. And the reason why I did it is because I was able to understand why people were suggesting to use a certain tool rather than the others. So category theory will help you write better code. But obviously, this doesn't mean that if you don't know anything about category theory, you cannot write good code. I'm going to stress this. You do not need to know category theory to write good Scala code. It's just that probably you're going to miss some understanding behind the concept that we are using. And also, you don't need to know category theory to write functional code. Functional code, believe it or not, is fairly simple. Don't use variables. Don't use mutability. And write functions that are total, and so on and so forth. There are a set of basic principles. Functional programming is not about category theory. But again, through category theory, we want to understand why functional programming is probably a better solution than others. And finally, as I was mentioning before, category theory just gives us the power to better understand why we write the code the way we do as Scala developers. OK? So what is this category theory? Well, the easiest way to understand what category theory is to ask ourselves how we reason. So we had to come to the venue tonight, right? So probably we took a train. So we probably took the blue line and then changed to a station and take the yellow line. So in a way, what we did is that we decompose our task into smaller tasks. Take this line, go to this station, take this other line, walk to the venue. But also, while doing this, we forgot about lots of details. So for example, we didn't think of we have to contract our muscles while we were walking, right? We know how to walk. We don't need to think about it. And that is exactly what category theory is about. So when we think, when we reason about things, we tend, as humans, we tend to do two things. Decompose and then compose back the single tasks that we have to deal with. And we forget about lots of details that are not really relevant. And category theory is the study of how things compose. What are things? Doesn't matter. It's not important what this thing is. It's important how he composes with other things. OK? But category theory, it's a scary term. It took me a while to get used to it. So I'm going to just rename it to arrow theory. This term doesn't exist. I invented it. Hopefully one day, people will start using it. But this is just because most of the people, as soon as they heard the term category theory, they get scared. Let's not call it category theory. Let's call it arrow theory. And the reason why I'm calling arrow theory is because you're soon going to realize that objects don't matter. The only important bit are the arrows. OK? So, what is a category? Believe it or not, that is almost all you need to know about category theory. So, a category has two objects, where object, probably I shouldn't say object, I would say two items that are linked by an arrow that has a direction. So in that example, A and B are objects, and the arrow is called F. What are these objects? Could be chairs, could be people, could be whatever you like. Obviously, we are computer scientists, so we have a much easier task than mathematicians, because we know that in our context, A and B are probably types, and F is probably a function. So the categories that we are going to talk about today are a really small subset that usually mathematicians have to consider. And obviously, once you have a category, you have some laws, some mathematical rules that dictate how to play your game. So the first rule that we have is that if we have an F that allows us to go from A to B, and we have a G that is a function, sorry, it's an arrow that goes from B to C. Yeah, you guys are never going to see this. Good. Then we know that we can automatically create a new arrow that is the composition of F and G. So the new arrow is going to be G after F. So mathematicians are a little bit weird. They do things the other way around. So they G after F. It's a little bit confusing. But after a while, you get used to it. So yeah, don't worry too much about it. It's just all this graph means is that if I know how to go from A to B, and if I know how to go from B to C, then I automatically know how to go from A to C. Okay? And this is called composition law. And moving on, the other rule that we need to keep in mind is the identity law. If we say this in really simple terms, we have an arrow that does nothing. So this arrow is called identity, and it basically, if we are in A, we can take the arrow identity and stay in A. So in mathematical terms, it means if we have, if we take identity of A, sorry guys, if we take F and then we take identity of B, it's the same of just taking F. And if we take identity of A and then F, it's the same of just taking F. It's really complicated, it's really confusing. All it means is just that identity is useless. So again, if you're a mathematician, I'm really, really, really sorry. Last rule of our game is that we can compose things in an associative way. In other words, what this means is that the green path is the same of the black path. What this means is that basically we can put the parentheses in any way we want. And this is basically a simplification simply because we have better things to do with our life. So we don't want to worry about the order of parentheses. We just, deal with things without worrying too much about little details. Okay? So we have seen what a category is. We have seen that we have some rules in our game. And these rules are the identity, that little arrow that does nothing. We have seen composition, that is if I have two arrows, I can automatically create a new arrow by composing the two. And then we have associativity, that is literally, I don't care about parentheses. OK? Cool. So all of this turns out that as developers, we do this all the time. This is nothing new for us. This is a practical example of a possible application of a category. So imagine you have a function that from a string returns an int. For example, let's call this function size. And let's assume we have a function that's from an int return a ball. And this function is bigger than 2. All we are saying is that if we have this function size and we have this function bigger than 2, we know that we can automatically create a new function that is transforming a string into a Boolean by doing size bigger than 2. Right? We do this all the time. And if you think about it, it's pretty obvious. We know that we can compose functions. But let's start a little bit about talking the meaty bits of this theory. And let's start with the simplest category that we can think of. So the simplest category that we can think of is just a category with one object. So let's repeat in our minds the rules that we just described. The first one was the identity. And it means that we have an arrow that does nothing, doesn't change the value that I have. And then the other rule that we said is that if we have two arrows, we know how to compose them. It means that if I have an arrow A and I have an arrow B, I know that somehow I can compose them and create a new arrow that is A after B, in this case. OK? So this is exactly the same of what we saw before. It's just that instead of having two objects, we just have one. OK? And as usual, mathematicians sometimes, they tend to give names to things. So they don't want to say category with only one object, because that would be too long. They just say monoid. So a monoid, it's a category with one object. OK? And again, we are talking about a category. It means that we have specific mathematical laws that we have to respect. And you're probably, well, you probably can read the text, but it's always the same three. We have an identity, we can compose arrows, and the composition of the arrows is associative. OK? Again, this presentation is not for mathematicians, so don't worry too much about the formulas. In my mind, these formulas are just the tests that I'm going to write. Don't get too upset if you don't understand the formulas. So again, this is something that, as developers, we do all the time. So for example, this is a monoid of int. It's a monoid. So if we take the composition to be the sum, we know that we can define a monoid as follows. We know that when summing a number, no matter what, we have a special number that in this case is 0 that is not going to change my value. And I know that if I sum any two arrows, I'm going to create a new arrow. So if I sum the arrow 1 with the arrow 2, I'm going to create a new arrow that is called 3. And if I sum the arrow 1 with the arrow 3, I'm going to create a new arrow that it happens to be 4. So you can see how this monoid is a representation of all the natural numbers in a really, really simple way. The general idea of a monoid is, given two values, how can I combine them together to get only one? So usually developers use monoids when they have a set of values and they need to get only one out of them. Okay? So what a lazy developer does every single time, we never implement things, but we define a type class. So we say, if you want to call yourself monoid, you need to tell me what is the identity, and you need to tell me what it means to compose two values together. So this is the definition of monoid. So a monoid, we are using type classes. I hope you guys are familiar with type classes. But the idea is that if we have a monoid, we need to define what is the identity value and what is the function to compose two values together. So a little bit of code. I'm going to give you guys 1 minute, probably 2, to think of an example of a monoid for int and a monoid for string. And then we will see how it goes. So I'm going to code a little bit with you. Out of curiosity, how many people managed to download the repo that I linked at the beginning? OK, cool. Nice. We have like 5 or 6 people in the room. So I'm going to code with you. Can you guys think of a possible monoid for an int, for example? I'll give you guys a minute to think about it. OK, cool. So as I mentioned before, I'm not a mathematician, so I'm not interested in knowing every single detail of every proof of why the rules are there. For me, the mathematical rules are just a set of tests that I need to write. So you guys are probably not going to be able to read the code. Don't worry. This is just to demonstrate that it's possible. But basically, you can transform those mathematical rules into tests that you can run that can verify that your implementation, your instance of monoid is correct. And in this case, we have used ScalaCheck, that is a library for property-based testing, to check that the identity, composition, and associativity rules are respected. So let's go back to try and write an instance of monoid for int. So as usual, lazy Scala developer, all we do is just say, OK, I'm just going to provide an instance of the type class. So one option will be to do exactly the sum, like we did in the slides. So there would be that compose will. How do we compose two integers? We simply sum them. Yes. And what is the identity for the sum operation? Well, that's just the number 0. Okay? Do you guys have any other possible suggestion of what a possible monoid for int we could have? A string, we will do it later, in a second. But another possible monoid for int, for example, would be demultiplication, right? So we decide what compose means. So for example, if we decide that when we say compose two integers, we mean multiplication, in this case, the identity will change to be 1. Okay? Let's try with string. So can you guys think of a monoid for string? Concatenation, well done. Yes, so we can just say concatenate two strings, and then the identity will be the empty string. Okay? Okay, cool. But as usual, don't trust me. Let's run the tests. So tests only, and then monoid. It's compiling, compiling. Yes. So what happened is that ScalaCheck generated some random numbers and checked that the composition, associativity, and identity laws have been respected. Okay? Everybody with me so far? Yeah? Cool. Okay, let's go back. Okay, this was fairly easy and a little bit too mathematical for my taste. Let's dive into the fun part. So now we know everything about a category, and let's see what funny things we can do by changing things a little bit. So what happens? We spoke about categories with one object, but obviously categories can have multiple objects. So what can we do with a category with more than one object? So let's assume that you have a flower and you have a triangle. And then somehow you know how to go from a flower to a flower and from a triangle to a triangle. But also, you know how to transform a flower into a triangle. Note that I could have used types here. I'm intentionally not using them because, again, for a mathematician, a category could be anything. So what happens if we put everything into a box? So what we are doing now is that we are taking the objects from the first category, and through a magic function, a magic arrow, we are putting them into a box. And we are mapping the rows of the arrows of the first category into the second category. Okay? So let's see what happens. So again, all we are doing is putting the objects into a magic box and then mapping all the arrows of the first category into the new category. Okay? So what does this mean? I mean, what do we mean with putting things in a box? So what we are doing is that we are adding something to my object. And this something is a box. And this box has information. So for example, a box could warn us that an object might or might not be there. Or a box might tell us that the object could explode any second. So you probably guys see where I'm going with this. But it turns out that this concept of wrapping values into types with certain meaning is something that we do all the time in Scala. So option is a box that tells us that something might or might not be there. So we need to be careful. Future is a box that is going to eventually contain a value. It's going to take some time. Well, it will get there. Try is a box that could explode any second. And list, it's a box that tells us that we could find 0 or more values inside our box. Okay? So in a way, what we are doing is that we are adding information about the values that we are handling. Believe it or not, this is exactly what a functor is. So mathematicians don't say that they are creating a magic box that gives us information. They just say that this idea of adding information about our values is a functor. We are lifting our values into a function. Okay? And as usual, we are talking about categories, so the basic rules still stand. So we have identity, composition, and associativity. The formulas are a little bit worse than before, but as usual, they are just tests that we need to write to make sure that our implementation makes sense. So if we look at this idea of lifting things, putting things into a box, what we are basically saying is that if we know how to transform a flower into a triangle, and we have a box of flower, then we must know how to produce a box of triangle. Another way of looking at this is that without opening my magic box, I can transform the value that is inside my box. Okay? And what a lazy developer does is that it defines a type class that says, if you want to call yourself a functor, then you need to tell me how, given a box of A and a function that transforms A into B, you need to tell me how to produce a box of B. Okay? So this is literally mapping one graph into the other. In really lazy terms, in Scala, when you have a map, you have a functor. Okay? So when people say, ooh, functors, functors, it basically means it has a map function with that shape. Okay? Cool. Let's give it a try. So let's try to define what a functor, let's try to define a functor for maybe. I'm going to try to clarify what maybe is, because it's a little bit funky. So it turns out that all this theory that I'm explaining to you doesn't use any powerful feature of the language. all it uses is algebraic data type. So as long as you, you are able to express some algebraic data types, that is all you need in order to implement functors. So to make things a little bit more interesting, I have created my own version of option. This is slightly copied from the Haskell people. Don't tell them. I could have just used option, but I just wanted to prove to you that we are not using any crazy function defined in the standard library. All we are saying here is that maybe is a container that has two possible statuses. The status just, that contains a value, and the status empty. Okay? So let's try to define a functor for maybe. I'll give you guys a minute to think about it. OK, cool. So same as before, those carry formulas are just tests that we need to write. So you can just use ScalaCheck to define tests that will make sure that the identity property, the composition property, and the associativity property are still in place. OK? And let's try to write an instance of Functor. So what we said is that Functor is basically the idea of being able to change the content of a box without actually opening the box. So if we think this in terms of option, if we have a value inside my box, all I have to do is to take that value and apply the function to it. If my box, if my option contains no value, sorry, bro, there is nothing I can do. So I simply return the empty box. In terms of code, that is translates to the following. So I receive a box of A, match, and I have to, it's an algebraic data type that has only two possible statuses. The status where I have, I called it just, I have a value A, and then I'll do something with it, and then I have a case none. Okay. Empty, empty. Good. So can anyone suggest an implementation for the case just of A? Don't be scared. OK, I'll do this one. Just FA. Awesome. I'll type it in a second. OK, cool. Still working. Didn't break a thing. Awesome. So just f of A. That is awesome. I find the value inside my, my box, and then I'm going to use it to apply the function, and then return it inside the box. And what is the implementation for the empty case? Empty. Awesome. Congratulations. We just implemented a functor for maybe. OK? Let's try to do 0 or more. 0 or more, it's, again, is the same as of list from the standard collection. But again, I wanted to prove it to you that we are not using any funky feature of the language. So all I did is that I said that 0 more has two possible statuses: 0, that contains no values, and the status 1 or more, that contains an object and then a tail of 0 or more. Okay? This is exactly the same as the same structure of list from the standard collection. Okay? Let's try and do that. So I'll give you guys a moment while I type. Can you guys see this at all? Yeah, looks good. Okay, so same as before, box of A, match, and then I have a case that I have 0, and I'll do something about it, and then I have case, and then I have 1 or more, and I have a head and a tail. Tail like this, yes. Okay. Same idea as before. We have a box that contains 0 or more values. If we look inside the box and there are no values, sorry, bro, nothing I can do. If inside my box I find at least a value, then apply the function to the value that I found, and then I keep going until I have no other values left. So how should we implement this? Any suggestions on the first one, the 0 case? What should I type there? Zero, yes. Awesome. And if I have a box that contains at least one element, all I do is that I say, well, I'm going to apply the function to the first element, and then I'm just going to do the same to the remaining elements. Okay? Sounds good? Awesome. As usual, never trust me. So we are going to run the tests. So if we do sbt install only Functor, hopefully they will pass. Compiling. Yes, it worked. Awesome. So good. We learned another little trick. Okay? Ready for the next step? My implementation probably is not type safe. So the cats and ScalaZ do it better. Absolutely, yes. It's probably not going to be stack safe. You're absolutely right. OK, new challenge, new case scenarios. So we discovered that we can put anything into a box. It could be a value, or it could be a function. So what happens in this case, right? We have a box that contains a function, and we have another box that contains a value. And somehow I want to open both of them and put them together to produce a box of B. So all the things that we can do so far is just look inside the box and change the value inside the box. We don't know how to open two boxes that are completely independent and merge them together, right? So type class again. Well, sorry, I skipped the slide. This concept of having boxes that are independent, that needs to be combined together, mathematicians call it applicative. So you have boxes that are independent, and you want to combine them together into one. OK? So there are lots of rules about these specific scenarios. But obviously, we're still talking about categories. That means that the user free, there are identity, associativity, and composition are always there. Not sure why composition is not there. It's probably a typo. Apologies. What we want to do now, we want to have the ability of look inside multiple boxes, take all their values, combine them together, and put them in a new box. OK? So 2 operations. Extract all the values, put them together, and stick them in a new box. And this is a possible implementation. So we say that if you want to call yourself applicative, you need to tell me how to put a value into a new box. We call that pure. And you need to tell me how I can, given 2 boxes, open them and combine them together. We still somehow want the ability to transform the elements inside. And it turns out that by using pure and AP, you can indeed implement map. And we are going to do that in a second. OK? But obviously, life is not that easy, right? What happens if my function requires 2 parameters instead of just 1? That means that I don't need to consider just 2 boxes, the one with the function and the one with the value. Now I have to consider 3 boxes. And what if my function has 3 parameters? Now I have to consider 4 boxes, and so on and so forth. Unfortunately, Scala has a terrible way of dealing with this. So you have AP2, AP3, AP4, AP5 functions, up to 22. So that is not ideal, but it's a limitation of the language. OK? But don't worry about it. We will focus on the easy scenario where our function just takes 1 argument. OK? So a little bit of coding again. Let's try to define map in terms of AP and pure. I know this sounds a little bit scary, but you will be surprised. This is actually what I call puzzle coding. That is, scream at the compiler for like 2 or 3 days, and the compiler is going to tell you that it doesn't work. And then suddenly, not only the compiler will be happy, it will also work. So you just have to play with types and make sure that they all fit together. So let's do that. I'll leave you guys a moment to think about it. OK. Any suggestions? OK, cool. Then it's not just me. It took me like 1 day to figure it out. So I'm just going to give you the solution, guys. And the solution is this one. So after you look at the implementation, it kind of makes sense. So map is just the same of AP if you put the function into a box. It takes some time to see this implementation. It's a lot of try and fail and compiler screaming at you, saying it doesn't compile. But this implementation is actually fairly short. I wouldn't say fairly easy and obvious. Okay? Cool. Okay, let's. So we have now a better idea of what applicative is. That is, again, having boxes that are completely independent and somehow we want to combine them together. Let's try to define an applicative for maybe. So as usual, type classes, type classes, type classes. I'll give you guys a moment. Okay. So how do I put a value inside the maybe box? Any suggestions? Yes, well done, guys. Boom. Awesome. Let's do the tricky bits. So I have two boxes. If they both contain a value, boom, I combine them together, I put them in a new box. If any of them is missing, then I cannot really do anything. I just return the empty box. So let's do. We have to consider both the boxes. Ooh, sorry. Still thinking about just. And just, hey. Okay. What should I do? Yes, awesome, just f of a. Just f of a. Cool. What happens if one of them is missing? I just cannot do anything, so I return empty. So what happens if they are both missing? Well, I still return empty. Empty. Okay? Awesome. We just implemented an applicative for maybe. Okay? Cool. I have no idea about the time. If we have time, we can do 0 or more. How much time do we have? We are going to skip it. Don't worry. As usual, same as before, we had lots of mathematical formulas that I couldn't really understand. But all it meant is that I had to write tests to make sure that the properties that mathematician tells me need to be valid are still respected. So we have identity, homomorphism, and so on and so forth. Okay? Cool. Everybody with me so far, yeah? Okay, cool. Ready to go a level up? We're getting stronger and stronger. And now is the crazy thing. Okay, what happens if we are in this situation? So we have a box of A, and we were changing the context of our box And we have, by changing the content of our box, we produced another box. So what we have now, we have a nested box. We have a box in a box. And we don't really know how to deal with that, because so far what we have done is that we can manipulate the content of a box. We can combine independent boxes together, but we don't know how to smash boxes, okay? So now we have another problem. So the problem is that we have a box of B, but actually what we want is a box of B. So what we want is to get rid of a box. And believe it or not, this is the concept of monad. Monad is just about smashing things together, okay? And if you are a mathematician, I so much apologize, okay? We are still talking about category theory, so we still have the three amigos over there. Identity, composition, associativity must be respected. All we have to do is that we have to, if you want to call yourself monad, you need to be able to map, and you need to tell me how I can get rid of a box that is translated into extending functor, because we need to map, and implementing a new function that is called flatten, that given box of a box returns a box. Turns out that this operation of mapping and then do a flatten is really common. So there is an alias that does both, so that our code is a little bit shorter, that is called flatmat. So flatmap is do a map and then flatten. Okay? Okay, but what does actually mean? So what this means is that if I know how to generate a box of B from an A, by using a flat map, I can go from a box of A to a box of B. If I know how to generate a box of C from B, I also know how to go from a box of C to a box of B to a box of C, and so on and so forth. So while before we were talking about boxes that were completely independent, now we are chaining all these boxes together so that we can go from box of A to box of D. So this is why flat map is really important for us. And this is because it allows us to give us order. So it's like a to-do list. It's just that flat map, it's a fancy way of saying basically the same. And this is really similar to code that we write daily in Scala, right? So we list what are the operations that we want to do in order, okay? So, turns out that a monad is actually a little bit more than just a functor. What we have seen in the previous slide is that a monad was extending a functor. That meant that it had a map function, and we were adding a flatten function. So the only 2 points that we had to define was map and flatten. If you are willing to change things a little bit and say, OK, I'm just going to define a flatten, and I am going to give you AP and pure from the applicative, we can create a monad that is a little bit more powerful than the one that we had before. OK? And we are going to do all these implementations together. So let's try to do that. So what we just said is that once you have flat map, all the other functions that are flatten, map, AP can be implemented in terms of flat map. Okay? Shall we try to do that? Yeah? Cool, let's do that. Cool. As usual, I don't care too much about mathematical formulas. You can just translate them into tests. They make sure that you are still respecting the mathematical laws that you need to respect in order to call yourself a monad. And now, boom. Let's have a look. Let me see my notes. Okay, cool. Let's try and implement flatten in terms of flat map. So my suggestion will be to look at the signature of the two functions and try to rewrite flatten in terms of flat map. I'll give you guys a second. Well, a minute, not a second, don't worry. Okay, I know it's a tough one, but any suggestions? So it turns out that this is how you do it. Don't worry if you didn't get it right. Again, it took me a while, so I don't pretend you guys managed to see it. But you know, once you look at the implementation, it kind of makes sense. Okay? What about AP? Can we implement AP? Sorry guys, let's do AP. In terms of flat map, and maybe map. Turns out we can, and this is the solution. So again, this looks fairly short. I'm not going to say easy because it's not. It took me a long time to see it. But it's that type of programming where if it compiles, it probably is right. All we are doing now is to use the existing function that we already have to make the types match. Okay? And the last one is map. Cool? Awesome. Okay, so we have seen how basically all we need in order to define a monad is a flat map. And flat map is the composition of map and flatten. In really imprecise terms, when in Scala people say, oh, it's a monad, they mean it has an implementation for flat map. Okay? Okay. Let's try to define an instance for monad then. Let's do it for maybe. Okay. So because a monad extends applicative, we can just say that the function pure is the same of what we have already implemented. And we said that pure is a function that just puts the value inside the box. So pure is just A. We have already seen that before. Can you guys think of a possible implementation for flat map? So what we said is that I have my box. If my box contains the value, super cool. I can use the function f to produce a box of B. And if my box has no values in it, then I cannot really do anything with it. I cannot apply a function. So I just return the box, the empty box. So box of A, match. We have two possible statuses. We have just of A, and we are going to do something, and we have case empty. So let's start easy. What happens if my box is empty? Is there anything I can do? What would you return? Yes, awesome, empty. What if I have a value? How can I produce a maybe of B if I have an A and I have an F? FA. Make sense? Congratulations, you just have implemented an instance of monad for the option type. Well, for the maybe type. Okay? Okay, cool. Everybody with me so far, right? So we have gone quite far away. We started with a simple implementation and then start adding rules on top of it. And we move from monoids to functor to applicative to monad. Okay? Now, a little bit of clarification on terms. Mathematicians have a really tough job because they have to consider a lot of categories that, as developers, we don't really have to worry about. For us, a category is just types and functions, nothing else. So when, as developers, we work with categories, all we are doing is that instead of creating new categories, we are still within the same category. So if flower and triangles are types, after we wrap them into a box, for us, they are still types. The same is for arrows. Arrows for us are functions. If we map functions, they still are functions for us. So when using a functor, if the source category and the target category are the same, mathematicians don't call it functor, they call it endofunctor. Endo means within, okay? And now the sentence that scared me for probably almost 2 years. Monad is a monoid in the category of endofunctors. This is a really scary sentence. It took me a while to understand it. I'm not going to try to explain it to you guys, but I would like to give you an intuition of why this is actually the definition of monad. Okay? So we have two important words in this sentence. That is monoid and endofunctors. So we have seen what monoid is, right? Monoid is the idea of I have two values, somehow I need to produce only one. Okay, so it's the idea of smashing things together. Endofunctors is just functors for us. Okay, so it's the idea of being able of mapping the content of a box without getting rid of the box. Okay? So in other words, what we are saying is that a monoid has an identity, and this idea of combining things together. So that is really similar to the pure function of monad and the flatten function of monad. So the idea of creating something new and the idea of smashing things together. And in terms of endofunctors, we have this ability of changing the content of the box. That's a map. That is all you need to define a monad. A monad is flatten. A monad is flat map. That is flatten plus map. And pure. So this is why a monad is the monoid in the category of endofunctors. Okay? Okay, cool. I hope I give you some idea of why that is a valid definition. Okay, cool. So it was a long journey. We have gone really far. I have bombarded you guys with lots of information, so apologies for that. But let's quickly review what we have discussed so far. So we have said that category theory doesn't care about the object itself. It's just the theory of how things compose. We have seen the simplest category that we could think of. There is the category with only one object, and that is called monoid. And we have seen that we can create new categories by mapping, by putting things into a magic box. That is the idea of functor. We have seen that we can combine independent boxes into one, and that is the idea of applicative. You could see this as having independent side effects that you need to combine together. And then we have seen this idea of monad that is about having boxes that needs to be chained together. You could see this as having side effects that depend on each other and need to follow a specific order. Okay? So this was a fairly hardcore introduction to category theory. But believe it or not, we only scratched the surface. You are not going to be able to read this, but this is just all the type classes that have been defined in cats. And we barely touched 4 of them. So there are so many things that we don't know yet that we could copy from mathematicians that could be really helpful for us. We just need to be brave enough and give it a try. But if you guys fell asleep during this talk, don't worry. It's fine. It happens to everybody. But the thing that I would like you guys to remember for this talk is that mathematicians teach us that it's not important the object itself. What is important in this case is how things compose together, how they interact with each other. So this talk is the result of me really wanting to understand why so many people were talking about this crazy category theory. So these are the list of resources that I used to learn about all of this. So if you guys want to know more about this, these are the resources that I would suggest. The first one, it's a presentation by Philip that he did at Lambda World, I think 2 years ago now. That it's an introduction to category theory for the working hacker. Bartosz has also put a really nice series of videos online that go into details of lots of concepts of category theory and how they can be useful for developers. If you guys want to have a look at that crazy picture that I showed to you with all the type classes, that is from Rob Norris, and that's the link to the infographic. But if you guys want to just want to give it a try, probably the best source is just the CATS documentation. The reason why it's the best resource is because they start with an example case scenario, and then they explain the mathematical principle behind it. So that is actually where I started, and then I had a look at the other resources. I'll put these lines online, so you guys are free to look at the code again, have a look at these resources, okay? And that was it. I hope you guys enjoyed it. That's my Twitter handle and my blog. And my suggestion, I know I gave you a lot of information, is just to code. So download the code, do the exercises, and hopefully it will get easier after a while. So thank you very much, guys. If you have any questions, I'm here.